big voltage at this end, if we had a plus and minus voltage here, we'd get a current going through here, right? All right. So this is how the braking system actually works, right? Or if we put a voltage this way, we'd get a current going crossways. All right. So let me write the first formula of the day. Now what we're going to do today is I'm going to give a few demos, and then I thought, since I hadn't done any yet, I just wanted to see how frustrating Wiley Plus was, because I've seen that you all started off with gangbusters, the first two assignments, and you've kind of gone, I'll get to it. So today I kind of want to get you back on track to getting those problems done. So we're just going to do it. There won't be a quiz today. We're just going to do, to make it worth your while showing up today, we're going to do most of the homework that I assigned yesterday. Okay, so we can get through so you can actually see how to solve these things, so that when you get in your groups a week from Friday and are doing the group test, you don't kill each other. You'll already know how to do things. All right. All right. I've seen great discussions though. I think this group test thing is working. I just wish I didn't have classes of 150 in the fall and winter. Otherwise, I'd do it more often. All right. But I guess my take home does the same thing. So anyways, as everyone's going, yeah, it's kind of a group test. Okay. All right. Now then, here we go. So here's the first formula. All right, we've already seen that F equals QVB sine theta, where that's usually perpendicular, so the sine of 90 degrees is usually 1. Okay? And now we're going to see F equals ILB sine theta. What? I is current, L is the length of the wire, and B is the sine. Oh, there she is. Good. I brought demos just because you said you like demos. Like seeing me screw up things. All right. So anyway, F equals QVB. So, and then F equals ILB. Now, how do you get that ILB? Because from this, you get dQ over dt equals I. Equals I. Okay? And L equals the length of something equals v times t, times delta t, the velocity times delta t. So if I put these two guys together, delta q over delta t, which is my I, times L, which is v times delta t, look what I get. I wind up with qv, just like we had up here. So that's why it works. Oh, no. I was getting ready to say something smart, like, yeah, I do, but that's okay. Yeah. There. Sorry. Yeah, that thing's annoying. Okay. There you go. This is one of those derivations that you all love so much. All right, so there's 2 parts. Now, let's take a look at this real quick, and then we'll get to some problems. All right? Here we go. Here's a braking system designed by English majors. Okay? Didn't work very well. All right? But English majors like it. You know why? What do you call an English major who makes money? A lawyer. All right? So they enjoyed it because there's lawsuits and everything else, so they made a lot of money. But they gave it to Physics220 students. They said, hey, all you got to do is put a copper strip in there and do this. Stops right at, whoa! Yeah, I like this one. This is cool. There's 2 magnets on the bottom. All right? So here's the deal. Not only when a charge is moving, when you get a current moving through a magnetic field, does it feel a force? Okay? But if somehow I've got a conductor and I move magnets over it, that's the same thing as getting the charges to move, relatively, right? In other words, when you're driving down the street or driving down the highway at 70 miles an hour, who's to say that that tree's not moving this way at 70 and you're staying still? Right? So it's the same concept, same idea. So therefore, that gets a current going and it feels a force. That's perpendicular. So here you go. Here's the right-hand rule again. You take your fingers in the direction of the magnetic field, hold it down. Now what it does is it's moving like this. It creates a current that's going this way. And so where's the force going? Back. And it stops it every time. And that's actually the braking system on the Mamba. All right? Because it works every time. Whether it's raining or whatever, it's going to work. And whoosh, boom. And the other, so that's one. So that's that F equals ILB type thing. But this time, instead of having, we're creating I by moving B. Okay. All right. So that's kind of an interesting thing. And then the next thing is that we'll look at today is we're going to look at torque in a thing. Here's some magnets. All right, on the end of a nail. You put it here on this battery, and you take the. This is kind of like Bill Nye the Science Guy now on YouTube. Anyway, then you take this, put it right here. What we're going to do is we're going to create some torque, and we're going to get into this today too as we go through our problems. And we're going to put a current on the side. So a current's going to be running on the side of this thing. Magnetic field's going up, so it's got a force going in, and it's going to turn this thing. It's going to work just like a motor. It's an electric motor that we're making here. This is the way they work. Just put it right there. And it starts spinning. Okay? Now, it's starting to get a little bit hot because there's resistance in the wire. Okay? And pretty soon there's enough charge that goes through there. It starts to get kind of warm. Okay? So that's another thing we'll look at today. All right. All right. So we can put all this aside. And this is kind of jump into what we're going to do today. We're going to do some homework problems. It'll be fun. All right. So let me get to them now that I've buried them underneath the good old overhead here. All right. In case you haven't been to Wiley Plus in a while, there's a new gift waiting for you there. Chapter 21 problems are there. Okay, and they are in no particular order. They're this. Here are problems 1, 3, 8. I almost ran out of my unlimited attempts on problem number 3 when I was doing it. So I understand your frustration. It was making me so mad. But you know what? It was me. It wasn't Wiley Plus. It was me. But that also lends to the fact that I think a lot of you would be much less frustrated if you could turn in a 10-point problem and you dropped a negative sign. Big deal. So you lose 2 points out of 10. You turn in and you go, okay, I dropped a negative sign, instead of getting the incorrect the whole time. Psychologically, it drives you batty. Especially you little pre-metters that are wrapped too tight. Anyway. All right, so there we go. I'm just kidding. Okay, and we got kind of. All right, extra credit. All right, 25 is your extra credit. All right, now then. So let's just take a look at some of these problems, like most of them. All right? And you go, well, wait a minute. We've only gone through half the chapter. Right. And we're going to be demonstrating the chapter as we go. Okay? All right, so the first thing we got to look at, here's in 21.5. Here's the big idea for the rest of the chapter for the most part. Okay? When I get a wire, okay, and it's got a current, let's say it's got a current going this way, then basically what that's like is this. Oh, I took the top off. All right, well, whatever. Okay. It's basically like this. Let's look at it from the front. All right, let's say this. The current's coming at you. All right, we're going to have the current coming at you. So if the current's going that way, then it's like this. All right, so we've got magnetic field all the way around here. Okay? And the magnetic field gets strong, and it's going in this direction. And the magnetic field gets stronger and stronger and stronger as you get closer and closer to the wire. All right? So here I came up with my own little, this is right-hand rule number 2. But I came up with my own little thing here. This is actually some when we get like 5th through, well, even high school kids coming through, we teach them how to make boomerangs out of paint sticks. It's pretty fun. Go outside. They actually work pretty good. All right? And they also keep your first wife away. But anyway, you put this here. All right? And Now then, magnetic field is going in here, and it's coming out over here. Okay? But it's going in a circle around it. Right? It's going, so at this very point, it's going in. Right? Now, if I rotate this thing, notice, now I've got my thing that's coming out at you like this, and then boom, it's going in. So when it's like this, it's going behind the board. At a point directly behind it, it's going that way, because it's all going in a circle. Okay? It's all going in a circle. So these are all vectors. If you take a circle, these are all vectors. They're going like this at certain points of the B field. Okay? And the force that it feels is ILB. Okay? The force is equal to amperage times the length of the wire times the magnetic field that's perpendicular to the wire. Okay? There it is. Okay. So that's section 21.5. And then we can add the sine theta thing there too. This is right-hand rule, so we got the current. So if the current's going, so let's take a look at, before we get into any more problems here, let's take a look at two wires. Current's going up on this one. Current is going down on this one. Okay? All right. Now then, remember, this is just the B field. This isn't the force that it's feeling. It's the B field. Okay? Now the force, and I'm going to go ahead and put that sine theta just so that we know that it's got to be that I and B have to be orthogonal or 90 degrees to each other, okay, for them to feel the force. All right? Or the horizontal or the vertical component. Okay, so we got I1 going up, we got I2 coming down, and let's say they're the same. Okay, now then, I1 is going to create a force on I2 because, okay, I1 is going up, so with I1 going up, we've got a magnetic field going in on it, correct? Got a magnetic field going in. Okay, yeah, now we go to right-hand rule number 1. All right? This becomes a gymnastics event, really. Okay, now, so we've got a magnetic field, we've got a B field going in, right? A B field on 2 caused by 1, we'll say. Okay, this is wire 2. The B field on 2 caused by 1 is going in. So the force on 2 caused by 1, B field going in, current going down. There we go. So which way is the force going? Out. So the force on 2 caused by 1 is going this way. Okay? And that would be I1 B21 times the length of 2. Okay? That's the force it feels.
Would we know B21 or
It'll be given to you. Or it'll say, if the forces are equal, what's the current? Those types of problems. And we'll get into that. That's why we're going to work these problems, because it is kind of crazy. So, now.
Can I ask you a question?
Sure.
So, you determined that the B field onto by 1 by that second right-hand rule?
Right. By right-hand rule number 2. You find the B field by using right-hand rule number 2, which is this, which is basically a curved hand. All right? So, if you've got, in other words, here's the way you actually do it. Here's I going up. I becomes your thumb, and you take your hand and you cup it like this. And so my fingers are going in right here. And if I come around, my fingers are going out this way. Okay? Which is the same thing this is saying. In and coming out. All right, so now let's take a look at what's happening here. There's a B field on this guy too. So this is coming down. Which way is this B field going? Caused by this guy. It's going in also. It's going in also. So it's going in, current's going up, so which way is the force going? The force on 1 caused by 2 is going this way. So if we hook if these two wires were hooked up to some kind of voltage where we've got the minus here and the plus up here and the plus here and the minus here and the plus down here by convention, then these two wires would go doink like this away from each other. They'd repel each other. If we get the current going the same way, what do you think happens? They attract. Okay. Right hand rule number 2. Okay. Okay. All right. First of all, let's do this real quick. Right hand rule number 2, B field. Gives you the B field. Right hand rule number 1 gives you the force caused by the B field. Okay? So in this one, so the B field caused by this wire, there's a magnetic field going in here, in here, in here, in here, and it gets weaker and weaker as we get away from the wire. Actually. Okay? The B field actually gets weaker and weaker as we get away from the wire. And so it's going in here. So now, got a B field going in. So we put our fingers in that direction. Oh, but the current's coming down. So the force, we're at right hand rule number 2, straight, it's coming out of the palm of my hand. It's coming out of the palm of my hand, so it's going that way. This one is going up, current's going up, so it's going out of the palm of my hand. So these two wires are repelling each other. If we have them go in the same direction, let's get them going the same direction. Okay. Let's see. We're going to go in the same direction. That one won't change, will it? Because this one's going up. So we got the so that we got this going in. Okay. So we got this going in. Current's coming up. So which way is the force going now? Right. It's going to the right. Let's erase this side so that force is going like this. And now that this is going up, whoa, this B field is now going in, caused by this guy. As he's going up, see how this B field's going in? So we've got a B field going in, current, coming out. B field coming out, thank you. B field coming out, current going up, so therefore the force is going in. So now they're attracted to each other. If you get the currents going the same way, they're attracted to each other. Get them going the opposite way, they repel each other. It's a strange little thing. And it's kind of overwhelming the first time you see it. You all look like you've had a good shot of Novocaine now. Good. All right.
So can you write the equation for what that force 1 on 2 would be, just so I make sure? Is it I2?
Yeah. The force on 1 would be caused by the force would be I1 caused I1 times the B1 times the L1 times the magnetic field on 1 caused by 2. This is wrong. So this is I2, L2. Okay? So it's the current is the current. The force, that's got to be the current caused by this. But this current is creating this magnetic field. Okay? Thank you. Help me work that out. B21 means this. This means magnetic field on wire 2 caused by the current in wire 1. Okay. Now, we can extend this idea, and then we'll do homework. to this. Extend this idea. Well, you already saw the torque thing. Okay, here's how torque works. All right, here's the torque. Let's say we've got a magnetic field. We've got a north, we've got a south, so we've got a magnetic field, and we got this little ET head in here. This little coil. Okay? It's got a current. All right? So there's a B field going across this way, and we've got a current that's going to be going up this way. We've got the same current's going to be going around here, and the same current's going to be going down over here. All right, foreign country. Let's do it louder. Let's just look at a square wire that's in the middle of a magnetic field that's going like this. Okay? This looks like a homework problem. And we've got the same I here, same I here, same I here, same I here. Now, what this does is this creates a force, makes this thing spin. Okay? All right? But let's be careful here. Let's be careful here. We've got, oh, you probably would like to know which way the current's going. I made the assumption because it was my problem. I had it in my head. I knew which way it was going. Okay, now then, let's take a look at this. Are these two guys, these two currents right here, are they creating any force at all? Yeah, the top and the bottom. Why is that? They're not perpendicular to the magnetic field, so it's zero. They're creating no force. Okay? They're creating no force. But these two wires here, like this one, is going up, so it's creating and the magnetic field's going this way, so because the magnetic field is going this way, and it's going up, it feels a force that's going in. Since this one is going down, and we got a magnetic field going this way, and the current's going down, it's feeling a force going like this. Right? So we got a force going in here, and we got a force coming out here. So what's that do? Spins it. Okay? Spins this thing. And here's the equation for torque. Torque is equal to the number of turns. In other words, and in this case it's only one turn. It's only one coil. It's not 4 turns. Okay? It's just one coil. Number of coil times the current in the coil times, just a second, I knew it, I knew what it was. Hold on. Yes. Times the area of the coil times B. NIAB. Okay. Looks like some kind of naval investigative unit, but it's not. All right. NIAB. This is number of turns. The one I just drew has 1. This is the current. This is the area. And this is the magnetic field. And of course, sine theta here. Magnetic field. Okay, good. Great. Now, let's take a look at some of your homework problems. We can get through quite a few here. And then at about 1, I will shift gears and teach you the rest of the chapter real quick so that you can see about solenoids and all that kind of stuff. All right, so here we go. Not to gaff you off too much. Now, as usual, I'll probably just set them up. Okay, here we go. Question number 1 says this. It says, at a certain location, the horizontal component of the Earth's magnetic field, horizontal, what's that? Oh, that's going this way. Okay. Horizontal component of the Earth's magnetic field is BE is equal to 2.5 times 10 to the negative 5th Teslas. Okay? And it's going this way, horizontal. All right, now, yeah. But it depends. It depends on what you have. In the book, everybody's thing is different. Everybody gets different numbers. Okay? And so now, it says I've got a proton. Oh, now that's screwy. It says the horizontal component is due north. Fine. Okay. Right now, Cutnell and Johnson says that that is horizontal. All right? So that component is due north. Okay? Yeah. A proton moves eastward with just the right speed so the magnetic force on it balances its weight. Find the speed. So I got a proton moving right here. Positive Q, but it's a proton. Oh, positive G. Very good. Anyway, but it's a proton. Mass of a proton is what? 1.67 times 10 to the negative 27 kilograms. G is equal to 9.8 meters per second squared. So F of gravity is equal to mg, which is supposed to equal the force of B, of the Earth's magnetic field, which is equal to QVB, where Q is equal to 1.6 times 10 to the negative 19 coulombs. Aha! I've got everything I need. I've got this, I've got this, I've got this, I've got this. The only thing I'm missing is V. So V is equal to mg over V over QB. There we go. Your magnetic field will differ. Your charges better not, because that's as small a charge as you get. Remember, charge is quantized, so can't get any smaller than that 1.6 times 10 to the negative 19. Ever. Ever, never. Now, problem 3. Problem 3 was cool because it kind of gives a practical thing on how television works. Okay? So you can go watch all those great summertime reality shows and watch your brain just ooze out of your ears onto your shoulders. All right? In the television set, it says electrons are accelerated from rest through a potential difference of 19 kilovolts. Okay. So my EPE, my electric potential energy here, is going to be Q times 19,000 volts. On my problem, on my Wiley Plus, it was 28,000. This is the one that drove me nuts. I worked forever on this one because I kept screwing it up. Now then, so the electric potential energy is that. Now, once it accelerates through that voltage, and it's gone, all right, and it's on the other side of it, is there any more electric potential energy? No. So all that's left, in other words, it converted all its EPE into kinetic energy. Exactly. So here's what we've got. We've got 1/2 mv of the electron squared equals QV. Big V. The voltage. So now, okay, and the question was this. The question was, the electrons, all right, they get accelerated through this thing, and they're hauling when they get on the other side. Okay, they're hauling, and then they hit a magnetic field that deflects them into the appropriate spot on the screen. It's kind of cool. All right, and with HD TV, this is up to about 50,000. That's why it takes a while. It's kind of a weird thing. with regular TV, have you ever been listening to like the Chiefs radio because you like Lynn Dawson better than who's ever doing the TV thing? And you notice that the radio is always behind the television? That's because television is going speed of light, radio is going speed of sound, roughly. All right, so there's a big difference. Okay? But in HD, it's completely different because all those capacitors and transformers that take that 120 to make it 50,000 take a while. Okay? For all that charge to get up there. Or the 117 RMS. Whichever. Okay. So, we wind up with VE then is equal to the square root of 2Q big V over M. M is 9.11 times 10 to the negative 31 kilograms. Here's where I kept screwing up because I was thinking of this problem and I kept putting the mass of the proton in there instead of the mass of the electron. If it was a proton, it'd be going much, much, much slower. And this thing winds up be going almost 1/100th the speed of light as they go in there. Okay? And then it deflects through a magnetic field. We want to see what the force is created by that magnetic field. It says find the maximum force. So that's the one at 90-degree angle. Okay? So the force then is equal to QVB. And we found VE right here. They give you B and you know Q. What did they say B was? 0.26, I think, 0.25, 0.28. 0.28 Teslas. That's pretty strong. That's a pretty strong magnetic field. Except that I gave you all a MRI problem on this. We'll just find the coils. And it's 7.43 Teslas in an MRI. Do you work with MRIs? No? Oh, okay. Have any of you ever had an MRI? Any injuries or anything? Did they make you take all your metal off and everything? Yes, because anything metal can become a projectile. Did y'all see that House adventure? It had one of the rappers in it. Can't remember. It wasn't LL Cool J, but it was the other one. Can't remember which one they had. But in this adventure of House, had this rapper on there. He had to get an MRI, and he had all these prison tattoos. What are prison tattoos made out of? Iron. The ink is iron-based. And so it's sucking all the ink out of his skin while he's in the MRI. It's kind of cool. Anyway, because of the force. Tremendous amount of force. Okay. What's that? Oh, it was exhibit? Oh, okay. Since I don't teach on Independence Avenue anymore, I've forgotten all those guys are. I left when 50 Cent was still big. He's long gone. Okay. Oh my goodness. I got carried away and assigned you problem number 8. Oh, it's wicked. It is wicked, ugly, wicked. Okay? And it's really not that hard. The only problem with it is, what's wrong with what we're doing? What is so different about what we're doing here versus what we've ever done so far in Physics 1 and 2? We're in 3 dimensions. The rest of the course has always been in 2 dimensions. Okay? Because we've got a magnetic field going out, we've got a current going this way, and we've got a force going this way. So we've entered 3 dimensions. We were kind of in 3 dimensions when we were doing torque and all that stuff, because we twist any, righty-tighty, lefty-loosey. That's 3-dimensional stuff. Okay. So here's problem number 8. And it's a little bit wicked in that basically what you have is this. You've got all your markers over here. All right. Here you go. You've got this going on. Okay. Here's the deal. I've tried to make this positive x look like it's coming out at you, but I didn't. What's that? Mm-hmm.
Yeah, that's.
Oh.
It's wider, closer to you, it's narrower, closer to you.
Yeah, we'll leave it here. I always had trouble with this. That's what kept me from being a great mathematician. I have no vision like that. Okay, now, I could do algebra and calculus all day long, but the upper level geometry stuff, whatever. Okay, now, here's the deal. Now, the z-axis is going straight up. So here's my, let's say this is my x and this is my negative y. And so z is up here, okay? And it is always, no matter how you rotate this around, z is always perpendicular to x and y, right? Okay, so what they did was they said, all right, along x you've got b, along the x-axis is 0.0411 Teslas. Along the negative y-axis, it equals negative 0.073 Teslas, or something like that. Yours will vary. All right? And then it says, hey, I've got a particle carrying a charge of 2 times 10 to the negative 5th coulombs. So Q equals positive 2.0 times 10 to the negative 5th coulombs. And it's traveling at, let's just say 420 meters per second. Okay, not bad, not bad. Now here's what I did. And now the question is this. The question is this. What force, find the magnitude of the net magnetic force that acts on the particle. Okay? Now you can do it this way. You can do it, you can go, well, f of x equals q v, because v is perpendicular to both the x and y, correct? Because it's going in the z direction. QV bx, okay? F of y equals QV by. And so what's that going to equal? What's F going to equal? Yeah, good old Pythagorean theorem shows up again. That's all. That's all it is. So the overall magnitude, the net magnitude, the square root of fx squared plus fy squared. Okay. What's that? Did it work? Oh. Really?
QVB sign for x and for y.
Oh. And it worked out? You know why? Yeah. Okay. Yeah. All right. I did it this way, and it worked out too. Because you wind up with, yeah, should, okay. All right, then they want the angle between them. How'd you get that? That took a while. That was tricky. All right, let's take a look at the top. Let's take a top view. Okay, top view, we've got V coming out at us. And here's X, and here's negative Y. Okay? Now then. Current's going up. Okay? We got a magnetic field coming down, current coming out at us. So which way is this force going? This way, right? So it's got a force going this way. That's the force caused by the X thing. Here we got the magnetic field going this way, current's going, and so we've got the force going down this way. There's the net force. Well, there's the net force. Now, what they want you to do is they want you to find the angle that is coming off that. They want you to find the angle that is coming off that. Well, that's not bad. Off the x-axis. Basically, but what you have to do is you've got to take the inverse tangent of Fy, of Fx over Fy. Trust me on that. Just trust me on that. Okay. All right. That was, I think, the only really ugly one that I threw out there. Problem 11. Oh boy. This is where a charged particle enters a uniform magnetic field and following a circular path. B is coming out of the paper. You got to determine, is the particle positively or negatively charged and all that stuff. And the particle has a speed. Determine the mass of the particle. That one, problem 11, is dealing with this. Is equal to R. The radius that is coming out is equal to mv over qb, where v is the velocity. Okay? Because we know, we learned this. I'm going to go ahead and erase this side. I'm just going to kind of start setting these up so that we can. Okay, so on problem 11, what you have is you got a uniform magnetic field that looks like this. Okay? So what's that uniform magnetic field doing? Coming out at you or going into the board? Coming out at you. So there you go. And then we've got a particle that has this kind of motion in it. That means it had an initial velocity coming in here like this. Now what they want to know is this particle, so its velocity is going up. So what they want to know is this particle positive or negative charged? It's negative charged, because if it's positive, it would go this way, right? Because magnetic field coming out at you, velocity going up, force should be going this way. But this has the force going that way. So it's a negative charge. And all your pictures are the same. Okay? And then they want you to figure out the mass. They tell you R, they tell you Q, they tell you B, and they tell you the velocity. And then they want you to figure out the mass. I think you can do that. Yeah. They give you Q, B, and V, and R. They want you to figure out the mass. The hard part is trying to figure out if it's positive or negative. Of course, if you've got unlimited attempts on Wiley Plus, you should be okay. You should be able to figure that out. But I don't remember doing that on Wiley Plus. But anyway. Okay, problem 19. If 19, oh my goodness, what am I doing to y'all? Assigning all these starred problems. I go nuts. I read, because I don't see the star when I'm assigning them from home. Because I don't have my book. I'm just reading what the problem is, and it doesn't have a star on it. So I don't know. All right, this is the same thing. It's the same thing. It's got a particle is moving into paper. It says, what must the magnitude such as, oh yeah. This one made me too heated because made me upset. Anyway, because I was thinking on problem number 1, here's the deal. Or problem 19, here's the deal. It's kind of a tricky problem. It's a little bit tricky. I've got a positive charge coming in here at V. Again, okay, magnetic field coming out, this going this way. So which way is the force going? On my problem, what problem is this, 19? Positively charged particle, okay. So, going this way, coming out at you, so the force should be going down, okay. Now, their question is this. So F of B, So the force on B should be Q, V, B, and going down. Okay? Now then, what they want to know is, they give you the speed, they give you the magnetic field. Just as the particle has a magnetic field, an electric field is turned on. What must be the magnitude and direction of the electric field such that the net force on the particle is twice the magnetic force? So the net force, all right, so all of a sudden they're going to turn on a magnetic field. All right, now here was my question. I thought they wanted the particle to go straight. So I thought the net force, but they don't. Basically what they want to do is they want the net force, the sum of the forces, it's got to go down to equal FB plus FE. And 2FB equals FB plus FE. So therefore, FB equals FE. So this is equal to Q times E, and this is equal to QVB. Guess what they give you? All this and this. What cancels? Q. It was frustrating the way they worded the question. All right. Problem 29. This is a good one. I like 29. Believe it or not, these things flow pretty quickly now. Kind of got them set up here. There goes problem 29 at you. We've already kind of done it. We've already done it a little bit. What they want is, problem 29 says the force on a current in a magnetic field. So here's what we've got. We've got this guy going like this. Aha! Got a little wire. The current looks like this. Current's going like this through it. Okay? And the magnetic field is uniform. Here's my B field. It's uniform going like this. Okay? And each segment of the wire, each length of the wire is 0.65, 29, no. Each length of the wire is 0.32 meters. So this is 0.32 meters, 0.32 meters, 0.32 meters, and this is 0.32 meters. Okay? And B, for mine, is 0.25 Teslas. B is equal to 0.25 Teslas. That's a pretty strong little magnetic field. All right? It says, all right, determine the magnitude of the magnetic force on each of the four sides. Okay. All right. Determine the magnitude of the magnetic force on each of the four sides. Okay, so the force, in other words, magnetic field's going up, current's going up. What's the force on this wire? Zero. Yeah, because I was sitting there going, wait a minute. Oh, yeah, there's no gap. So it's zero. Okay? Zero here, zero here. What about this one? Up, this way. Which way is the force going? It's coming out at us. Okay? So the magnetic field, so the force is equal to ILB. Right there. We know I. They're going to give you I. They give you L, and they give you B. That's pretty nice. And then down here, is it going to be the same down here, but it's going to be doing what? It's It's going to be going the other direction. But all they asked you was the magnitude. So the magnitude's the same.
Can you tell me again how you determine if it's going in or out from a
What? If what's okay. It's right-hand rule number 1. Force, you do right-hand rule number 1. So if it's going up, if it's parallel to the magnetic field, if the current's parallel, no force. But this one's perpendicular. So put your fingers in the direction of the magnetic field, and then put your thumb in the direction of the current, and you see that the force is coming out. Right here, it's like this, so the force is going in. It's coming out of the palm of your hand. All right, 38. 38 to the spot. Okay. Oh boy. 2 coils have the same number of turns. Here we go. Torque. 38 is a torque question. 38 is torque. Okay. And we know that torque is equal to the number of turns times the current times the area times the magnetic field. They always say in this book, they always say it's perpendicular. So we'll just let the sign of 90 be 1 and assume it's there. Okay? Now here's what the question asks. The question asks this. It says two coils have the same number of circular turns and carry the same current. Each rotates in a magnetic field, and coil 1 has a radius of 5 centimeters. Okay? So there are 2 coils like this. You know, they've got several turns, but they've got a radius. Coil 1 has R1 is equal to 5.0 centimeters, which equals 0.05 meters. Be careful, in Wiley Plus they ask for the answer in centimeters, so you got to convert back when you're done. Okay? Otherwise you'll get very frustrated. You go, I know I did this right. Okay? R2 and N1 is equal to N2. I1 is equal to I2. The B fields are different. B1 is equal to 0.18 Teslas, and B2 is equal to 0.42 Teslas. And R2 I don't know. That's what I'm after. And B2 in my thing is equal to 0.42 Teslas. But here's the deal though. The torque of 1 equals the torque of 2. Well, that's not bad. We can do this all day long. NIAB equals NI, or B1, A1, equals NI, A2, B2. Lots of stuff cancels here. Okay? Lots of stuff. Okay. So like this cancels, that, and we're after the R that's inside of here because they're circles. Okay? So it's A1, B1 over B2 equals A2. And you can figure out an A2 is equal to pi R squared, R2 squared. So you can get those down and you can find R2. Not much trouble. But that's just showing you the torque. Now, before we move on, 48, 52, and 60, last 3 problems of your homework assignment there, you got to learn something new. One last thing. Okay? You got to learn some more about B fields. Okay? Strength of an electric field. Strength of an electric field. A B field. Okay? It depends on the geometry of the current. Depends on the geometry of the wire. Straight wire. Here it is. Straight wire. The B field, here's a straight wire. And we're going to have the current going up. Okay? We're going to have the current going up. About beat that horse to death. Hopefully this one will work. Okay? Got a current going up. So what's my B field over here? Is it going in or out of the board? Remember? It's going into the board. Right-hand rule number 2 has it going into the board. I've lost my little thing. But anyway, so it's going into the board. And it's a distance r from the wire. So B, the magnitude of the electric field it's going into, is equal to this. Mu naught I over 2 pi r. You've got a new variable to worry about, or constant, universal constant to worry about here. That is the permeability of free space. Okay? Have you guys seen this in lab? And we're like, what is that? Okay. Well, it's the permeability. Mu naught, this guy, is called the permeability. Oh boy, why did I start spelling? I don't know. There we go. Permeability of free space. Okay? And he is equal to 4 pi times 10 to the negative 7 Tesla meters per amp. He's a funny thing. And if you look at this, if you look at him over here, look, if I multiply him by amps, the amps cancel. And if I divide him by meters, the meters cancel, and I'm left with what? Teslas. Okay? But he's a funny little animal. So you know what I do when I'm using this one? If you notice, the 2 pi, you got 4 pi in the numerator and 2 pi in the denominator. I just cancel and get 2 times 10 to the negative 7. Kind of works better, easier on calculator. But the calculator will negate it anyway. It'll see pi and doesn't really matter. Okay, so that's for a straight wire. Now, let's put a wire in a loop. And that's why I brought this guy. Let's put a wire in a loop. Which problem are we on? 38? Oh, we're already up at 48? Cool. So we just got 3 to go? And we'll get them done. I can't believe it. We'll actually get the whole chapter and all the homework done here. And I don't know if you learned anything, but at least you got enough you can at least get this. All right, now, let's say this is a loop of wire. Okay, the direction of the current is going to be my thumb, as it always is. And I'm going to grab this thing like this. So the current's going this way. There's a magnetic field going inside here that's uniform. Inside this deal. Okay? There's also one coming outside, too. If I make the solenoid long enough, there's no magnetic field coming. But there's one. But the magnetic field's going in the direction of my fingers. So this way, with the current going around this way, the magnetic field's coming out at you. Okay? If I want the current to go the other way, if I want to turn my thumb the other way, how do I do that? I'm going to stand this way. Yeah, if I want the... Damn it, still going the same way. Okay, there we go. If I want the current going the other way, now it's where's the magnetic field going? It's going in. It's going direction of my fingers. So you just grab your coffee mug or whatever when you're doing these problems. You can figure out, okay, that's for a loop. That's for a loop. All right? And here's how, for a loop of wire, so this is for a straight wire. This is for the B field for a straight wire. Strength of the B field for a loop of wire is equal to this. B is equal to the number of turns, I'm pretty sure. There better be a number of turns. Or I quit. I'm just going to quit, call it a day. Is it number of turns? Yes, had to be. I knew it had to be. Okay, it's number of turns. Now this looks funny. mu naught times I. So far everything's okay. Times 2r, which is the radius of your thing. So let's draw a coil going like this. let's have the current going this way. So I is going that way. All right, so I is going that way. So which way is the electric field going, or the B field going here? Right. This one is just like this. No. There we go. Okay. I got it. Well, this is clumsy as hell. Current's going that way, so the B field's curling. It's coming out at you. Right? You wouldn't know I draw it the wrong way. So it's coming out at you. Distance r from the center. Okay? And actually the B field, that's at dead center. The B field is actually a little bit, as we get closer to the wire, it gets a little bit stronger.
If the current is moving counterclockwise, then as you move along,
That's okay. I've been there. I've been there with that. Okay. What?
Why do we use pi in the denominator?
It's part of the derivation. It's part of the big derivation that they don't even bother to do in this book. But good, yeah. Kurt caught it. Yeah, the pi is gone. The only difference between this and this is this pi and the number of turns. It's the only difference. Okay? Because basically what we've done is we've taken a straight wire and we've bent it around, and so when we multiply it, when you do that calculus, the pi winds up, you wind up with a pi in the numerator, and it cancels out one from the other. Okay? All right. And then last but not least, if I have a solenoid, this thing is a solenoid. Okay? This thing is a solenoid. So I'm going to grab it here. Solenoid, the B field of a solenoid means it's wrapped with wires. These are wires wrapped around this thing, really tight. And it's how we make inductors, okay? Because they can store magnetic fields in them. All right? As long as they got current going through them, they got a magnetic field in there. All right? And for a solenoid, the B field for a solenoid is equal to mu naught times n. Well, actually, they write it this way. N, which is the number of turns per meter. N is the number of turns per meter. Number of turns per meter times mu naught times I. Okay? So, let's take a look at problem 48. Problem 48 says this. It says, okay, the magnetic field produced by the solenoid in a magnetic resonance in an MRI, okay, systems designed for measurements on the whole human body has a field of 7 Teslas. So, let's do the solenoid thing. B equals 7.0 Teslas, okay, and a current. It's got pretty big current too, I imagine, of 200 amps. That's a pretty good little current. I equals 200 amps. Okay? They want to know how many turns per meter it is. On problem 48, they want you to know, figure out how many turns that is. I think that's pretty easy. If you know B and you know I, and you can look at, and there's the permeability of free space, I just kind of wanted you to see how many turns there are on that thing. It's a lot. It's a lot. It's an incredible magnetic field. It'll pull the braces right off your teeth. I mean, it will. Cut braces, you can't get an MRI. Oh, here's my boomerang. Okay. All right. Now, okay, problem 52. Problem 52. And then problem 60 is just like it, for the most part. Okay? Problem 60 is just like it. All right, here's 52. So we're going to, it says a very long straight wire, okay, a very long straight wire is running tangent to a loop of wire. Okay? Like this. So here's the situation that they've got on problem 52. Here's the situation. All right, so we got a straight wire like this, tangent to a loop of wire like this. Okay? Now then, they say this. The directions of the currents are such that the net magnetic field at the center of the loop is 0. Both wires are insulated and have diameters that can be neglected. How much current is there in the loop? Okay. So, in other words, okay, let's assume the wire is going this way, and it's got 0.12 amps. Yeah. So I of the wire is equal to 0.12 amps. And it's going up. So it's got a loop, if I use my thing here, okay, so it's got current, the magnetic field is going in. All right? Okay, so if the magnetic field is going in, I want this to come out, so which way should my current be going here? Counterclockwise. Right, I should grab it like this. Okay? And so it should be going around like this, counterclockwise. All right? So this loop is going, is this counterclockwise? Yeah. So there's the eye of the loop, which I don't know. But they equal each other in magnitude, correct? Because they want B of the wire plus B of the loop equals 0. So therefore, B of the wire equals negative B of the loop. But magnitude-wise equals B of the loop. Okay. So, the B of the wire then is mu naught I of the wire divided by 2 pi r. And this r is the same for both the wire and the loop. Equals mu naught I of the loop divided by just 2r. A lot of stuff cancels there. To figure out, and what you got to figure out is IL. Okay? Now then, I got 4 minutes, basically. Not having a quiz. The benefit of coming to today's class is you got the homework kind of done. Your numbers will change to protect the innocent, but due to Wiley Plus. But the problems are the same. The stuff is the same. Okay, here we go. Problem 60. Notice I didn't do the extra credit column. You know why? I can't do it. I haven't looked at it yet. Never do physics on the fly. Never think, oh, I can do those problems, and just look at them, and then you come in and you go, uh-oh. I don't know how to do this right now. It's kind of embarrassing. All right. Okay, so here's problem 60. And it's Ampere's law. It's the same thing. It's the same thing that we've just been doing. Basically, we've got 2 wires. Okay? We've got 2 wires that are side by side like this. One has an amperage of, my problem 60 is 28 amps, and the other one's 12 amps, and R equals 0.72. Okay, we want to figure out a distance from both these wires. R equals 0.72 meters. We want to figure out what the B field is right here. They're both straight wires. Okay? Now then, one wire, I1 equals 28 amps. And let's let I2 equal 12 amps. Okay? These are straight wires. What's the formula for the B field? B equals mu naught I over 2 pi r. Okay. Now, well, all it says is you want to do it once if they're going in the same direction, and then you want to do it again, find the B field if they're going in opposite directions. If they're going in the opposite direction, is the B field going to be less or greater at that point? It'll be less, right? Because if they're both going in the same direction, they're adding to it, going into the board. Okay? They're both adding to it. If one is going in and then the other one's coming out, then it will be trapped. Because B fields are vectors, and so you can add them, especially if they're going in the same direction. Then they're real easy to add. Okay, so that's all that one is. So what do you think the easy way to do it is? It's going to be this. One answer is going to be this. What do you think the other answer is going to be? Minus. Yeah. Okay. All right. Okay. There you go. That's the way you do those. Now I feel good about moving on to chapter 22. Have fun and laugh. And then have a safe holiday weekend. No class Friday, but there's a lab because they can't do it on Monday. Kidding.